by Goffredo Chirco, who's going to talk about multipartite entanglement of random spin networks in quantum gravity.
Okay, thank you, Thomas. I'd like to thank first the organizers for the possibility to talk. I mean, so far it's been a really beautiful conference. So today we start hearing about the importance, the impact of entanglement in quantum gravity, and what I'm going to present to you today is like a simple exercise from the quantum gravity point of view. In fact, it's something more related to quantum space, so it's toward the quantum gravity, which on the other hand involves some complicated techniques from quantum information theory, which then would be simple from a conceptual point of view, but maybe technical. So let me show. So the point is, okay, it was amazing to have Jan de Boer today and Hal really introducing this context for me. And yeah, entanglement has been, I mean, a very key conceptual feature in quantum gravity in the last decades, maybe more than 10 years now. And I mean, from the first step, passing from the Beck-Steinhausen entropy-area-entropy relation to, can you hear me? Right. To the Ryuta-Kanagi formula, okay, for in IDSFT, then, you know, suggesting in this sense the possibility to reconstruct space and space-time, in fact, from the entanglement structure of the boundary, in that case in IDSFT, down to local holography, which Laurent already discussed in a new context now, from the original work of Mia and Takayanagi, to the new, I mean, information that we are gaining from a lot of techniques implied from quantum information theory implied in what is the quantum black hole paradigm and information paradox, but you know, like replica wormholes techniques and so on. And down to the very radical idea then, eventually quantum, I mean, space and time can be emergent from entanglement, okay? And so why the title of my talk? So most of these deduction conceptually came from the use of entanglement entropy. So from essential bipartitioning of Hilbert spaces, and we see that already now. I mean, exactly this bipartitioning is what is you know, focusing our attention on the issue of separability, finding algebra subsystems, and the way we glue, okay, subsystems or a portion of space-time in particular in quantum gravity. But I mean, going beyond these results also means to, you know, investigate more from a quantum information point of view, like structure like multipartite entanglement or different measures. So in this sense, and in particular, going to non-perturbative and Becker-independent contexts, like a loop quantum gravity, as we saw this morning, is a pretty precious tool. I mean, to test somehow these ideas in a very quantitative way. Okay, so in loop quantum gravity we have, I mean, we know that we don't have a full theory. We know we have issues with dynamics, but we also know that we have a very reliable description of quantum space, at least, and we have a clear Hilbert space description. Okay, so in particular, okay, as we saw today, in loop quantum gravity we have a kinematic Hilbert space, okay, which is an L2 space of function defined on holonomies of the SU2 Ashtekar-Barbero connection, okay, where we, at least at the first step, we can impose SU2 gauge symmetry. So we have SU2 gauge symmetric functional, and so we have this particular structure, the space, which is sum over irreducible representations of SU2 of something which factorize. Okay, yeah. So on this Hilbert space, we know. I mean, nowadays also, so we have what we already discussed. So the fact that we cannot factorize the space, but we can at least look at each superselection level and see, I mean, quantities can be defined, and this is what we are going to do effectively. So we are going to measure entanglement at the level of each sector. Okay. So so in order to somehow leverage or acquire techniques from quantum information theory, in the last few years we slightly changed our description of spin networks, in a sense. Also, we tend to see spin networks, so purely derived from quantum gravity, for instance, as tensor networks, as peculiar SU2 gauge invariant tensor networks. And in fact, this is a way to see them that which allows to directly transfer our know-how in condensed matter to our states here. So our states here are basically contractions of some physical state which lives, or is supposed to live, on the nodes of a spin network in terms of project some edges which basically glue nodes among each other. These edges, in our case, are related to some physical some physical description, which is so they are not purely they're not just gluing nodes among each other like in a standard tensor network. So they're not purely virtual objects, but they are related to Wilson lines. So they carry, information about holonomies. So we have to take this into account, because this in particular brings information about topological non-trivial connectivity, for example, of the graph into play, something which is never discussed at the level of, for example, of random tensor networks results. Okay, so in this case, so we have our basic state is something which has a core which lives on these nodes, which can be arbitrarily generically entangled. Okay, and then there is a connectivity which is induced by the support of the graph on which our functional finds support. Okay, so this is a standard spin network, but what we know it is are interested in are in fact boundaries, and it's more and more interesting to look at corners effectively, what were discussed so far, even if in a much rude way here. So to spin networks basically which are cut out of something of actual gauge invariant wave functional. Okay, so imagine you have your wave function which is a gauge invariant object here. So everything is contracted and gauge invariance is imposed locally, but then achieved at the global scale, and then you cut out the region. Okay. Now suddenly you have these degrees of freedom here coming out, which in this case are just like spin magnetic indices, but they would be like dressed properly in a context like the one Laurent discussed, which define a boundary. Okay, define a boundary. And when you have a boundary, in fact, your functional is not anymore valued in C. It's something which lives in an Hilbert space, which is the boundary Hilbert space. So the very spin network itself, by itself defines a bulk-to-boundary map. Okay. And the properties of this bulk-to-boundary map, like the holographic properties, this is something which really recalls like a quantum error correcting code once you put a bulk on it. No? And so the properties of entanglement, of maximal entanglement of these edges, are related to properties of isometry of this map, and you can study these properties as we did, for example, or Eugenia Colafranceschi did recently, and Simon also discussed about these points. Okay, but so this is our starting point in a sense, and what we want to add to this basic structure, which is really in one-to-one, can be mapped in one-to-one to a standard tensor network object in condensed matter, is the fact that we have non-trivial holonomies. Okay, so this object really carries non-trivial holonomies, and in fact, if you have non-trivial holonomies, this means that this structure actually carry curvature. Okay. So at the end of the day, so we want to see how much information from the bulk we can recover from the quantum correlations that we have on the projected state on the boundary. So this is the point. So how do we do that? So we have to squeeze somehow all the information about the curvature into degrees of freedom which are very simplified and can be described in terms of in simple terms. So we act by standard techniques in loop quantum gravity. So we use like a reduction by gauge fixing. We exploit gauge fixing at each node in order to squeeze locally, if you want, in a given region of a certain radius of your network, all the non-trivial information about the holonomy on vertices. And we imagine we can do that distributedly, uniformly along through the network in order to have something like that. So something where your non-trivial holonomy, so curvature somehow, is attached to each node. This is not enough, of course. This is already somehow too complicated. We want to partially coarse-grain to encode this information about the holonomy and non-trivial holonomy in something more simple, which is just what we call a tag. This was, standard literature from Etera, Levine, and actually Laurent itself. So we have this holonomy. We imagine to coarse-grain this graph by unfolding the intertwiners. So these intertwiners are just a recoupling of spin representation associated to these Wilson lines. Imagine. So you can always think of unfold the Hilbert space of your node, and once you did that, you can trace over it. So you can coarse-grain, in a sense, the information about the holonomy, and you end up with a spin now, which is reminiscent of what you were carrying out. So there is a closure defect spin, so a spin which measures the amount of flux that you are, eliminated by integrating over the holonomy. And this is a closure defect, has to do with clearly with curvature, as today I'll explain to us intrinsic curvature piling up at the node. Okay, so once you have this object, basically you can see these spins as basically measuring the non-closureness at the nodes, which now become not anymore gauge invariant. And in this sense, you can think of this hedge spin inside. So you have some spins at the boundary, so boundary degrees of freedom, but you have some spins in the bulk, which are still boundary degrees of freedom in a sense, because they are associated to some open region, okay, in the bulk. And in this sense, this allows you, in this very simplified model, to define an Hilbert space, which is, again, a direct sum of something which factorize of a boundary, which is an external boundary and an internal boundary. And since this internal boundary reflects the curvature of the associated to the non-trivial holonomies of the graph, then, of course, what we're going to do, we're going to measure the correlations between internal curvature and external boundary. Okay, so your state now will be a bulk-to-boundary state, which though lives in an extended boundary, and you can see that correlations about the actual boundary and the inner boundary carry all the information about the bulk. Okay, so how do you recover this information from, for instance, a purely boundary observer. So the take we take this point of view. So we consider a boundary observer. We make a random measurement in order to simplify the state again. So we partially trivialize the bulk, okay, in this sense by using projecting vertices with random vertex states, and we end up with a density matrix, okay, which is just a contraction, the bulk contraction of bulk and edges as before, plus this projector, okay. Now we work, as I was saying at the beginning, with fixed J's, so it's again a very simplified setting in the context of loop, so we lose basically a lot of degrees of freedom, and we look at a tree partition now. A tree partition is related now to bulk, tag spins, Hilbert space, and boundary spins, which are now divided into two parts. Okay, so imagine you have you are an observer at the boundary. You don't see the tags from the bulk, so you don't see the curvature. You just see the boundary, and you pretend to do like a bipartition of the boundary. So you have an environment which will affect, okay, the correlations of your boundary. And this is a typical setting of a tripartite analysis, which is, by the way, also the one that is used as a starting point for the replica wormhole in a DSCFT. So actually, those are very, very similar techniques. So which measure of multipartite entanglement in this case we use? We use a measure which is called negativity. That's why, how many minutes? A few minutes? 1 minute? 0 minutes, okay. This is a measure which is well suited for mixed states, because now we have an environment, so our boundary is not anymore a pure state. We need to use this quantum negativity. This is a faithful measure, though it's not a measure which is quantitative. You cannot actually tell how much entanglement there is. I mean, you can say whether a state is not separable if negativity is non-zero. Okay, so is a witness of entanglement in a sense. Okay, so let me go very quick. So we, of course, as you have seen many times in this setting, you never go for actual calculation of quantum entanglement or entanglement entropy, and even in this case entanglement negativity, you go for Reni. Generalization of it, and then you take the analytic continuation to k equals 1. Okay, this allows to simplify the calculation in a sense, and also the fact of starting from a random tensor network here plays a fundamental role, because in a typical regime, basically we know that the expected value of our quantity will match the actual value. We can prove this point, but also, I mean, we know that we can approximate this Rene negativity in terms of basically a ratio of partition function, okay, which are given by the trace of the momenta. So the momenta of this partially transposed density matrix. Okay, let me skip the details, but let me at least show you the details, the details of the results. Okay, so at the end of the day, like this complicated calculation, which basically is a diagrammatic way to compute these partition functions, which will be the partition function of a generalized Ising model, where basically on the very spin network, I mean, the randomness allows you to map the quantum system to a classical system where spins are replaced by a permutation operator. We end up with an action. This action has a topological and an intertwiner related that we call physical contribution. Okay, and the negativity. So the topological part is the one that we focus on here, and just to show you that the negativity for a very simple graph like that can be computed and gives you a very rich entanglement phase diagram, if you want. So we have three. So depending basically on the dimension of the three subsystems, so boundary A, boundary A1, boundary A2, and bulk environment, you have three configurations. So one is a whole configuration where basically the environment is so big that basically you have a disconnection, or if you want a complete thermalization of the boundary. The second point is a bipartite regime, so where the environment is so small that basically you are back to a bipartite setting. And then the last one, which is the most interesting one, which is an island.
Sorry to interrupt you, but can we go to the conclusion?
Yes. So this conclusion is that here is the conclusion. So in particular, in a specific regime, which is the island regime, you see that the negativity is proportional to the area, okay, minus linear correction depending on the tag contribution. And so since our initial general goal was to basically measure geometric quantities in terms of quantum information or quantum information inspired quantities, then this is very interesting, because at the end, I mean, you realize that what is telling you this result is not just something related to the area, but is something related to the curvature. So since we start from injecting curvature in our problem, then we see that we are able to recover curvature from this analysis. So, okay, basically this is a summary. So we tried these techniques, and we saw that these techniques apply to our setting. We are measure like quantum negativity, so reflect the topology, the connectivity of the graph. We find area scaling behaviors like Ryuta Kayanagi in our system, but also like we have a bulk term, which is basically the analog of quantum corrections in the Ryuta Kayanagi in a DSFT, and essentially, yeah, with a multipartite, so with a tripartite setting, so going beyond entanglement entropy, we are able to add an extra ingredient to our geometry entanglement correspondence, which is about curvature. So curvature can be expressed as in terms of relation of what I didn't show you, mutual information and bipartite entanglement entropy. Okay, and yeah, now there are more speculative things which may be discussed maybe later if you have some questions. So thank you. Sorry for being so squeeze.
Okay, thank you. Due to lack of time, I propose we immediately go to the discussion session where we can ask questions to every speaker. So if there are questions to any speaker, please.
This is a sort of question/comment for Laurent in his talk. So this dressing to the boundary, or basically to the corner, implicitly assumes that there are degrees of freedom that correspond to these edge modes in the theory. And it's not really clear that those should fundamentally be part of the theory. That's part of the reason why in thinking about dressing in some of the earlier work, we looked at dressing off to infinity, for example. And of course, when you consider all the diffeomorphisms, you're sort of ignoring the diffeomorphisms that move the boundary. So could you say a few more words about how we should think about these basically edge modes, and whether in some sense, they're just ad hoc degrees of freedom that you introduce, and whether you think they have some more fundamental significance.
Yeah, thanks for the question. Yes, I agree that. Yeah, first, so the thing which is really established is that you have this kind of a symmetry group here, which is there at the corner, and then that the action of your symmetry group on the states. So you need, it's clear that you need to add some dressing in order to represent this group. So essentially, these dressings they are there as states of representation of this group.
But it's not just dressing, but you have to fix the region, and then you're breaking the diff symmetry.
Exactly, you have to fix the region, you have to break the symmetry, and now I want to say, well, if I want to talk about a state inside, I have to pick a representation, let's say, of that symmetry group. Effectively, when I do that, I kind of I now have states of different which have the same, which are transformed into discharge. So what you're asking is, in the way I was presenting, I'm saying, okay, I'm just adding them there to fix the location. So now, and in fact, it relates to what you're doing or what Philippe is doing too. So now there's the questions of, well, how can I think of these dressing modes as some kind of physical mode? So either, attached to some fixed boundary, like Philippe is doing, or attached to kind of infinity, or maybe to I naught, if really I don't care about my region. In my case, recently, because I'm thinking of an interferometry experiment, inspired by Catherine picture, I'm thinking maybe I want to kind of attach them to the diamond itself in some sense, right? So make them a bit more local, and then ultimately, yeah, I want to think of them as something physical in the sense. And one evidence for that, and it's not an evidence, but it's kind of a hope, is this type 2 to type 3, which is something very simple. It's just that if you add one dressing, if you just add one mode, which is the one conjugated to the modular Hamiltonian, there's many more modes that you need to kind of fix. But if you have this one mode, somehow you have a mechanism to resolve UV singularity, just based on the fact that it's about putting part of the phase space, the fact that this location of that sphere cannot be exactly well defined. And then, I think it's an interesting question of finding the physical mechanism in which to which they respond, right? Whether you attach them at infinity, whether it attached to the center of the interferometer, or whether you can even think as some kind of fundamental extra object. Does that answer?
I think so. Yeah, I think that, well, in some sense, the dressing is physical, but the question is whether you're dressing it to something physical. And, maybe that's part of the...
Yeah, exactly. Right now, I was describing as some kind of quasi-local mode. And then the question is that if I have two different corners and they talk to each other, then you need to have some kind of relationship. Yeah, I agree. But we will agree that it's physical. Now, with respect to what? With respect to the setting, I think that's the discussion.
Let me maybe just quickly follow up on that, since you already mentioned this. So in our works, we actually took more a global perspective on these subregions in the sense of being embedded in the global space-time. And then you can indeed, for instance, also along the lines of your works of dressings, define the edge mode fields actually as coming from Wilson lines that are attached to some asymptotic structure or something like this. But then from the global theory, you can actually do some kind of post-selection procedure where you reduce to a subregion theory. And so from the global point of view, these edge mode fields are not new degrees of freedom. They're just built out of the field content that's already there. But when you do this post-selection to a subregion, they actually appear as new degrees of freedom for the subregion phase space. And why are they new? Because they have support, for instance, in the causal complement of the subregion, and so you can vary them independently. And so that actually also explains why the symmetries that you get on the corner, why they, for example, also are consistent with symmetries of the global theory. So they just correspond to when you do such symmetry transformations, it basically corresponds to changing initial data in the causal complement. So and then if you do it this way, you actually recover all the things that Laurent and so on did in their original works.
Any further question? Do you mind?
Okay. Anyway, so the question is, I like the point of view of starting with, I'm going to see an exercise to do local physics and have a part of the space-time and the other, the exterior. But then from that point of view, eventually I have to probably try to cover more of space-time, like if I have a Cauchy surface divided into with some charts, and I study the causal diamond of each chart, then you have two that intersect, and then they should like complement each other. But at the beginning you said that you were going to have the same algebra and the same everything for things that they have the same topology, you know. So if you have two balls, they intersect. So can you comment on that?
Yeah, it's interesting you mentioned topology. So it's true that if you have a sphere topology, the algebra is universal. Of course, if you have torus, I never mentioned that, we never use that, but you have central charges, for instance, that appear.
But
if you have GSG, you would have...
If you have two balls, they intersect and they join into another ball.
And I think your analogy, so what I'm saying is that somehow the symmetry group I record is the same. The modes that these guys transform are these edge modes. Of course, what happens is you want to do a quantum gluing of states, which, I view a little bit like when you have two open sets and then you find the overlap between them, you glue them, and then what happens at the quantum level, so it's like almost like a quantum coordinate charts. What happens there is that, as Philippe was saying, you have to take the maximally entangled states, of course, which, the entanglement is carried by this edge mode and it kind of disappears. In the same way that if you have two open sets, you glue. Now it's kind of an analogy, and it would be interesting to see whether there's a quantum Riemannian picture. Is that where you're going about it? But the universalities maybe that I was talking about is the universality of the type of charts I have to use to glue the two subregions, because it's kind of a local property.
My question is, what happens if you have a black hole inside? If your sphere is a horizon?
Yeah, so if the sphere is an horizon, a lot of things simplifies, because then that surface. So, the case where the relationship between modular geometry and symmetry was clear was before this kind of general case, was always in the case where you have a Killing vector field, right? So you have a symmetry. So if you have a symmetry and your horizon, your entangling surface is preserved by that symmetry, then you don't need gravity for the modular Hamiltonian to be geometric. In general, the modular Hamiltonian is a completely non-local object that you have no control about. And so that's why people just focused on horizon before, because it's only this particular, and there you don't need gravity. Okay? But gravity, allow you to free yourself from just restricting to horizons. So in horizons, it's much simpler for sure.
You mean, but does it help you with any questions about black holes? My understanding
well,
is that you would seems to be everything is regular. You don't have any problems.
My perspective there is that the intuition that came from the black hole is kind of universal, maybe along the line of Bianchi, Myers, and more recent works. In some sense, we all felt that there's something universal about this. Why do we care about black hole? It's just one solution. Otherwise, if it's not something universal, it's just one solution among GR for one particular surface.
Saying, black holes are not special at all, In your, your picture,
no, they are special. They are special. They are very special because they are.
Can you see something? Can you infer something from your analysis about the black holes? Or for you, it doesn't matter. Is it a black hole or just empty space?
Well, I think a lot of people have inferred most of what they can do on canonical horizon, the thermality of it, and the geometrical entropy. All of that has been, done and done.
No, but I'm asking, in your approach, do you get something new? Do you see something new?
Well, what I get new is that I want to say that this correspondence between geometry and entanglement, if you want, and statistics and geometry is quasi-local. It's not just global.
So maybe one more question, preferably to one of the other.
Hey. My question is for Goffredo. So I know you didn't have time to go through all the stuff.
About it.
I just wanted to know, like, how did you recover the curvature notion in this tripartite entanglement picture?
Yeah.
Like the idea, like, did you do some coarse graining? How do you recover? Yeah.
So the idea is that basically, so you had squeezed in your description. You have a tripartite system, and one of these parts is somehow related to curvature. Okay, and then you ask, can I recover this information from the entanglement of the rest? Okay, and the answer was yes. I mean, this is an entanglement measure via this quantum negativity, which is a new measure in a sense. And is it sensitive to that? And the answer was yes, it is. And it was very nice how it came out. I mean, because basically in this particular regime that so the three regimes that I showed are nicely related to the properties of separability, or if you want, along the line of, I mean, what of the idea that no entanglement means no connectivity of space, where space-time maybe eventually. You really see that in the three cases. You see that when your environment is very, very big, then your boundary get thermalized basically, and this looks really like what we have at the Big Bang, for instance, or at some singularity. We have a large curvature and something around it which looks thermal. Then you lose. I mean, you squeeze your environment, and I mean you pass to a regime where the three parts balance somehow, and there is where you see that the negativity, which turns out to be the mutual information, actually, is related to the bipartite entanglement minus a correction. But if you think of, since you have in loop quantum gravity a nice mapping between bipartite entanglement and area, then you can show that this mutual information as an area minus something is really like analogous to the way you define Riemannian curvature in you know, by approximation even in the discrete case. You have something like a ratio of curved area which would be mutual information with the area of a flat ball, which would be bipartite entanglement, 1 minus something which is the intrinsic curvature or Riemannian curvature times some extra scale which we don't know how to. So I mean, what we find, and I couldn't show you properly, is that I mean, having three parts gives you more information about I mean, the dual geometric description of your quantum correlations. Okay.
Okay, I think we should close the session. So let's thank all three of the speakers again.